So our next lecture will start the design of compression member. Okay, very simply or briefly we'll check what is the design steps of compression member. First of all, initially say what happens whenever we are going to design a compression member. The load will be given to you, and maximum what information will be available to us is that what type of section we are going to use. It may be available, this may not be available to you. Okay, so in such case, how to start? In general, what we do initially, because since we know only the load, but what is the allowable permissible stress, that is also not known to us. That means sigma s is not known to us. So initially, you have to assume some sigma s value. No specific guideline is given like that. When the load is a bit, it's a lower side, okay, and when the load is a bit lower side, it is assumed that only single section will be enough. In that case, then we can assume that initial value of sigma sc is approximately 80 to 85 MPa. We can assume. Okay, so that is a single sections. Okay. Or any kind of single like it may be a single channel section, it may be a single eye section, or it may be a single angle section, whatsoever. Now if you see that the load is a little bit on the higher side, that means single section may not be enough. In that case, what you can do, you can assume sigma sc value as 110 MPa, the initial gas. Okay, once we have that value, then our next step is we need to know because now see the load is given to us. What is the compressive load? Now sigma sc we assume something, so from here what we can do, we can find out what is the area required. Okay, what is the area required for this compression member irrespective of the type of the section. So you can say area required is equal to the given compressive load divided by assumed permissible compressive stress, reliable compressive stress. So whatever the p value is given, sigma sc you have assumed here, so you can find out what is the area required. Once you know the area required, then your job is to go to the steel table and find out a suitable section. How to choose the suitable section? The suitable section will be such that whatever the area available on the suitable section, that area must be at least little more than the area required. That means you have to go to the steel table, find out a suitable section where the area available must be greater than area required. That we have done in your step number 2. Once you choose this section, then find out its slenderness ratio. If slenderness ratio, how to find out slenderness ratio is equal to L effective divided by minimum radius of gyration. So check what is the minimum radius of gyration of that particular section. Now depending on the support condition of the column, you will be knowing what is the effective length. So from that you will find out what is the lambda max. Okay, lambda is basically the maximum slenderness ratio. Fine. So this is our step number 3. Now what to do in the next step? Step number 4. Now once we have the lambda information, then what we can do, we can go to our code book IS 800 1994 and we can go to our table number 5.1 that is given in the code book, and then from there what you can do, we can find out the actual value of sigma sc. How to find out? I have already discussed the previous class that this table comprises of 2 important parameters. There is one is the lambda value and another is the different grade of the steel. Say in our case we are using Fe250 steel. Okay, and this side you will find the lambda values are given 10, 20, something like that. So see what is the lambda value you got and find out corresponding sigma sc value from this table. Okay, so with respect to Fe250 steel and the corresponding lambda value, get the value of sigma sc. If directly you do not get, then do the interpolation part. Fine. So now this is the actual sigma SE or actual allowable compressive stress for this section. Now what is your next job? Next job is to find out the load carrying capacity. So what is the load carrying capacity of this section? Next step number 5, load carrying capacity of this section is equal to P is equal to whatever the sigma SE just we have calculated in the previous steps multiplied by the actual area available of this section. So this is your load carrying capacity of this section. Okay, now what to do? To check this load carrying capacity, this P value, whether this P value is greater than or equal to P design. If this is the case, then you can say your design is safe. That is the number one thing. Now you have to take care also some other information. If some reason this P value is coming less than P design, then no doubt you have to redesign it. How to redesign it? You have to choose another section whose sectional area is more than whatever the sectional area you have chosen in the previous steps, or choose a section whose radius of gyration is more than the previous one. Okay, so if you choose a different section and then again you have to redo the same steps and check that your P value must be more than P design. Now there is a question, how much? If you say that this P value is substantially higher than the P design, that is this given design load, then your design is not economical. Okay, so you have to reduce the section. That's why suddenly you cannot take a higher value. You have to start with a small increments, like say your design load or cross-sectional area required is 600. Then you start with very close value of the 600. So 610, 620 mm square area. Check. If it is failing, then go for the next higher increment. Otherwise, if 600 is required and you suddenly take a value of say 1000, your design may be safe, but it will be ultimately an uneconomical design. So that part you have to take care. And second thing is that there are various sections are there which will satisfy you. Now suppose if you see that one section is giving you, say your desired load is 100 kilonewton, and if you take say one light section you have used or medium beam section you have used, and it is giving a load of after calculation you are getting say it is 100 say 5 kilonewton. So no doubt your section is safe. Now there may be another heavyweight sections or another lightweight sections are there with the same sections, but what happened, you are getting a load or your calculated load is say coming 106 kilonewton. So since with the same section but with the heavy section was giving 105 kilonewton load and the lighter section was giving 106 kilonewton load, then why should I go for a heavy section with the same cross-sectional area? I will go for a lighter section. So I will go with the lighter section and I will use it. So what I mean to say that suppose you have a section of ISMB 225 and another section say ISWB 225. No doubt in these two sections the small difference is there that their weights are different. Okay, one case weight will be more, another case weight will be less. Now if a lesser weight, just 1 minute, now take an example of say IS 250. Okay, that was wrong. So in a, say ISMB 250 is also giving you a calculated load which is more than the design load, and ISWB 225 is also giving you a calculated load which is more than the given load or more than the design load. Now which one is to be chosen? First of all, what you have to do, you have to see that which section is economical section out of these two. Now how to know which one is economical? Whose weight per meter length is less, that will be the economical section. Okay, if you see the code book, that is steel table, what you will find, For case of ISMB 250, its weight is given as 37.3 kg per meter, whereas if you look for ISWB 225, its weight is given 33.9 kg per meter. Okay, so which one is economical here? Economical here is the second one. Now you design it and check out of these two, which one is giving you higher load. I mean to say higher P value. Suppose this is giving a P value of 35 kilonewton and this is giving a P value of say 37 kilonewton, and your desired or your design load was say 33 kilonewton. Okay, so both cases your section is passing. You can take ISMB 250 also, or you can take ISWB 225 also. But which one will you choose? You see there, even though this is giving a higher load, but still this section is the economical section because its weight is less. When less materials are provided, so it is the economical section. So we'll choose this section rather than choosing this section. Though this is also passing, this is also passing. Okay, both are satisfying our criteria, but still we'll choose this section because it is the economical section. So we have to check that part also, that we must choose an economical section rather than choosing an uneconomical section. So what I told earlier, that suppose you need 600 mm square area, suddenly you cannot take a section with 1000 mm square area and you cannot say that your design is safe. In this case, the design is not an economical design, and here somebody may say that your design is fails because you have to save the money. So that is also another objective of the design, that your design must be economical. Okay, so this is how we can do the design of a column. Okay, so whatever the design steps right now I have discussed, these are also applicable in case of strap. Okay, so let us take an example quickly and see what we can or how we can apply the concept that we have learned in this class. Okay, if you have the notebook with you, just write down the question. I am just quickly telling the question. Suppose you are asked to design a column member which is say its length is 3 meter, length of the column is 3 meter, and it's carrying a load of say 3000 kilonewton. Okay, sorry, say 300 kilonewton, is not 3000 is very high. Okay, say this stage we will go for a smaller value. So say this is a 300 kilonewton load and the length of the column is 3 meter. Now what we need to know? We need to know what is the support conditions or what is the end condition. Let us assume that the column is effectively held in position at both ends but not restrained against rotation. Effectively held in position at both ends but not restrained against rotation. So it means this type of column is this one, right? Held in position at both ends. Okay, so that this distance is given to you how much? 3 meter, and it is carrying a compressive load of 300 kilonewton. Okay, so effectively held in position, that means this position is fixed, it cannot go up and down, but not restrained against rotation. So horizontal movement is permitted. That means it will start bending from here, right? So bending will be from this location to this location. That's what we have discussed earlier. And then in this case, what is the effective length? Tell me. Effective length is L effective is equal to nothing but 1L. Okay, so that means what we can say, that for this problem our effective length is nothing but equal to 1L, that is same as the length of the column, right? 300 kilonewton is not so higher load. Okay, or even say right now we do not know anything. So what we will do? Our first steps, let us assume some sigma SC value. I am assuming a sigma SC value 80 kilonewton. Let us see what happens. Initially we do not know whether it is a very high load or whether we will say we are not experienced. We have not done a single problem till now. So we do not know what to do. So let us assume that it is like that. Okay. Assume a sigma SC value of 80 kilonewton. So what is the first steps? I said that you calculate the area required. So how to calculate A required? A required is equal to given load divided by assumed sigma SC. What is the given load? Given load is 300 kilonewton. This is not kilonewton, man. This will be MPa. Sorry, permissible stress, Newton per millimeter square, divided by 80 MPa. If you divide it, it will give you the area required. So what is the area required? In this case, area required is equal to 3750 mm square. So it means what? You need a section from the steel table whose area will be minimum of 3750 mm square. So now you have to go to the steel table and find out a section. We can design it using various sections, but since though I have not told in the problem, let us assume that the problem is the load is axially loaded. Axially loaded means the load is applied exactly at the center. So which type of sections if I choose, then the load will be, suppose I want to use a single section. In that case, if we take a I section, we can simply apply the load. Means it will be a, I am not saying that we cannot do it with a channel section. Channel section also we can do. We can apply the load exactly at the center. But both sides, and it will not be a symmetrical one. So if you have a single section, better to choose the I section. And I section, if we apply the load exactly at the center part, it will be symmetrical. Symmetrical means both sides, the dimensions will be equal. So let us assume a symmetrical I section. Okay. In a symmetrical I section, the load is applied at the CD. So go to the steel table and find out an I section whose area will be minimum 3750 mm square. So if I go to the steel table and I search it, what I can find, that there is a section called ISMB 225 at the rate of 31.2 kg per meter. Okay, the given area is equal to 3972 mm square. So as per our requirements, this is more than 3750 mm square, so this section must satisfy. So what are the other parameters that you need to know from the steel table? That is the minimum radius of gyration, R minimum. Okay, if you see this, you will find that R minimum is about RYY, and this value here given is 23.4 mm. Okay, so once we have this information, then what we need to find out? We need to find out the lambda value, that is slenderness ratio. What is slenderness ratio? Slenderness ratio, lambda is equal to L effective. L effective we have calculated earlier, 3 meter. 3 meter means 3000 millimeter divided by 23.4. Okay, so how much? If you divide this by this, you will be getting the slenderness ratio, and this value is coming out to be 128.2. Okay, so another condition is given. What is the limit of slenderness ratio? When no earthquake or wind load is considered, the slenderness ratio for a compression member must be less than 180. So this is the first check that yes, the slenderness ratio is within the limit, that is less than 180. Now what you have to do? Either you have to use the Rankine equation or the equation that is given in the steel table, that is sigma S equal to 0.6 FCC divided by FCC to the power n plus Fy to the power n whole to the power 1 by n, or you have to go to the code book that is given table number 5.1. Okay, for this lambda value and for a Fy value of 250, you have to find out what is the value of sigma SC. Okay, that we can easily find out from there. Okay, if you see the code book, then the values are easily available and we can find out those. Okay, there are two values are available. One value is 57 for 130 and 57 for 120 and then 64. Okay, so these are the 57 for 130. Okay, if you see this table, that you will find for 130 lambda value, the sigma SC value is given as 57, and for 120 lambda value, the sigma SC value is given as 64. So what you have to do? You have to do the interpolation between these two together. Okay, so for doing interpolation, first write down the minimum one, 130, then plus the difference between these two. So what is the difference between these two? 57 minus 64 divided by 130 minus 120. Something is wrong here. Here we cannot write. Where we have to write down the value of minimum one, that is 57 plus 57 minus 64, corresponding value you have to write 57 minus 64 divided by 130 minus 120. Okay, then multiplied by what is this value? This value is written for 130. Something wrong I have written. It is not like that. First we have to write down the value for minimum. Minimum is how much? Minimum is 120. For 120, what is the value? Value is 64. Corresponding to the minimum lambda value, what is that? Plus the difference. Difference is 64 minus 57 divided by 120 minus 130. Okay, multiplied by, initially for which I have written 120. My objective is to get for what? 128. So 128.2 minus 120. Okay. So if we do the calculation, how much it comes? It is coming out to be a value of approximate calculation. What is that value? That value comes out to be 58.26. Okay, ampere. So just let me quickly give you the information. How do I calculate this? Okay, initially what I have a value of, for 130 my value was how much? 57, and for 120 lambda the value was 64. So what I write, my target value is 128. So I have written first corresponding to the minimum value, corresponding to the minimum of lambda, that is 64, whatever the value, plus the difference between minimum minus maximum, or you can write down difference between maximum minus minimum, both are same. I have written minimum lambda. So minimum lambda, what is the corresponding value is minimum lambda minus maximum lambda. So minimum lambda corresponding sigma c value is 64 minus 57. Okay, this is corresponding, this is corresponding. Multiplied by, then give a bracket. Write down your target value. What is your target value? 128.2. What is your minimum value? Already corresponding to which you got the minimum? Corresponding to 120. So minus 120. Do the calculation. This value is giving you 58.26. Okay. So this is the lambda value that we got, 58.26. Okay. So that is our required. Once we have this lambda value, then what is to be done? Once we have the sigma SC value, then what is to be done? Tell me. Now what we have to do, we have to calculate the safe load. So what will be the safe load? In this case, safe load is equal to area available multiplied by the calculated sigma SC. So what is the area available that we have written earlier? What was that? That was 3972 mm square multiplied by sigma SC, that is 58.26 Newton per mm square. So mm square get cancelled. Ultimately you will get this value in terms of what? Newton. What is this value coming? This value is coming 231 then 000. So divided by 1000, that will give you in terms of kilonewton. Okay, I have directly found out this value in terms of kilonewton. So for that, what I do, I need to divide it by 1000. So this value is giving 231 kilonewton. What was your desired, or what was your design load? Your design load was 300 kilonewton. So this value is coming less than 300 kilonewton. So what we can say? Our design is not safe. Since the design is not safe, we have to redesign it. How to redesign it? To do the redesign, now you have to choose another section from the steel table whose area must be more than whatever we have chosen. Okay, or its radius of gyration must be more than whatever we have chosen earlier. Okay, if you got the steel table, then try with this one, ISMB 250. Okay, ISMB 250 at the rate of 37.3 kg per meter. Okay, its area given in the steel table is 4755 mm square, and R minimum, that is RYY, given in the steel table is 26.5 mm. Okay, so what is our objective? Our objective is to get the lambda value quickly. Lambda value is 3000 divided by 26.5. So that comes out 113.2. This is also less than 180, so we can say it is safe. Okay, then quickly we will go to the steel table, IS 800, and find out the sigma SC value. You will find there are two values you will get. One is the corresponding to 120, and another is corresponding to, okay, if you see this table number 5.1, you will find corresponding to 120 you have to get, and you have to get corresponding to 110. Corresponding to 120, just now I have written earlier, that is 64, and corresponding to 110, this value is 72. Okay, so simple logic, what I said, suppose our target is 113, so what is the lesser than 113 is 110, so write down for 110, 72 plus, find out the difference between these two. I can write like that, 72 minus 64, then what you have to write here at the bottom, 110 minus 102 multiplied by, what is my target? Target is 113.2, and what I have written already I have written 72, that is for 110. Now if you do this calculation, this is giving a sigma SC value of 69.44 MPa. Okay, see, it is very close to 110, so a value of sigma SC you will get corresponding to the closer value of 110. closer value 110. What was the value of 172? So closer value 69 is close to the 110. Okay, so it is something like that. An approximate idea will give you that whether your calculation is correct or not. Now once you got the sigma SC value, then multiply with the cross sectional area, that will give you the safe load. So this was the cross sectional area that we have chosen. So my safe load is equal to this value multiplied by 69.44 Newton per millimeter square divided by 1000. Okay, so that will give you the value in terms of kilonewton. Divided by 1000 by that time. So this value, how much you are getting? This value, if you calculate it, it is coming out to be approximately 330 kilometers. So my 330 kilometers is more than 3000 kilometers. So what we can say, my design is safe. Right? We got a safe design value. I will just show you another. Okay, see, we need 300 kilometers, we got a 330 kilometers, so it's fine, it is safe. You cannot say that it is not safe. But just see with a different section. Okay, just now you remember that we have used one section and we got this value, and we are just trying with a different section and see what happens. Let us take a section, say earlier I said ISWB. Let us take ISWB 225. ISWB 225 at the rate of 33.9 kg per meter. Okay, what will happen? Earlier case, how much load we have? What was that section? That section was carrying a load of 37.3 kg per meter. Now I have taken a section of with 33.9 kg per meter. Okay, what is the area of this section? This area is 4324 mm square. No doubt this area is also less than my previous one. Okay, previous one was 47 something. Okay, because I have just escaped to show you that whether our section is satisfying. We are satisfying, but still there are some other section also there in between that section may satisfy. So that's why I am taking a section with lower value of cross-sectional area. Okay, what is its minimum R minimum, or if you say that is equal to RYY, and this value is given in the steel table is 32.2 mm. Okay, now what you do, you find out the lambda value quickly. Lambda value, if you find out, that is 3000 divided by 32.2, and that's giving you as 93.2. Okay, it is 93.2. So since the value is 93.2, so this is also less than how much? 180. Our target value is 180 maximum. So this is less than 180, so we can accept it. Okay, once we are accepting it, then what we have to do? We have to go for finding out the sigma SC value. So how to find out the sigma SC value? Lambda is 93.2. You go to the code book and find out sigma SC value for a lambda value of 93.2. So for that, what we need? I need to find out for 90 how much, and for 100 how much. For 100 the value is given as 90, and for 90 the value is given as 80. Okay, so you just do the calculation. Okay, I am not showing once again here. You check it out. 86.8. Okay, our value was 90. Okay, so for 93.2, if you do this calculation, it comes out approximately 86.8 MPI. Okay. Now what you have to do? You have to calculate the safe load. How to calculate the safe load? Safe load is the cross-sectional area, that is 4324 multiplied by 86.8. Okay, 4324 multiplied by 86.8. How much it gives you? Just check it out. This is coming out to be 375 kilometers. So this 375 kilometers is once again what we can say, more than 300. Okay. So now see, What we got? We got two sections whose safe loads are more than the design load. What are those two sections? One section what we got, that is IS MB 250 at the rate of 37.3. If you do this, then what is the safe load coming? Load carrying capacity is coming as 330 kilonewton. Okay, if we use IS WB 225 at the rate of 33.9 kg per meter, what is the safe load? Safe load is coming 375 kilonewton. Okay, now see, both cases our design is satisfying. Both cases the value is more than 330. The first case, that is whatever we have IS MB 225, that case the load was how much? 231 kilonewton. That was less than the 330, so that is automatically rejected. Now this case, both cases it is satisfying. What we did, just to save our time, we have taken this value first. It is satisfied, but still there are some other values whose area are less than the value that we have chosen earlier, or say unit weight is less. Unit weight is less means area is less. Okay, so still there are some values which is carrying more load than the 330. Then why should I go for this section? I will go for this section. Okay, so even the area is less, but still it is giving a higher value of load carrying capacity. So this is more, both are more than 300 kilonewton, but still I will choose this section. Okay, so that means what we will do, we will recommend that, or simply we can say the suitable section for this given problem is IS WB 225 at the rate of 33.9 kg per meter. Okay, so this is how we can design the problem. Okay, we can design a section. Same steps you need to apply for the strat also. Only thing is that you have to check what type of struts, what are the support conditions, and based on that how much permissible compressive stress we have to take, whether we have to take 100% of sigma SC or 80% of sigma SC, that you have to check, and how to take the effective length depending on the end condition, that is whether rivets are used, single rivets, or welding are used, or both are used. Depending on that we have to take the effective length. That we have to take care, otherwise the remaining design steps are almost same. Okay, go through this part properly. Next class we'll see the built up column. Okay, we'll start the built up column from next class. Built up column means using multiple sections, as well as some other additional members we can use in the column, that is called what is called that battens and all other members, splicing and all those things, and we have to see how to use those battens and all those things members, and we'll try to finish this remaining part in the next 1 hour lectures. Okay, till then, okay.